Hi everyone, I'm Ophélie Chupin, and now let's find out when a hotspot of wave power is not a hotspot for wave energy conversion. Wave energy conversion is a type of renewable energy that consists in harvesting energy from the ocean waves. Currently, the problem is that too many times researchers select the hotspot for wave energy conversion based on high wave power or energy location. We will demonstrate today how can a hotspot of wave power not be a hotspot for wave energy conversion, and more precisely, how to overcome the hotspot selection based on high wave power. For that, we will present a framework which main structure is based on whether the bathymetry is considered as uniform or not. After the introduction and the presentation of what is a wave energy converter, we will see what is the selection guideline in the presence of a uniform bathymetry, and otherwise the decision-making process handled by the decision tree. Please be aware that you can follow the presentation advancements thanks to the little icons on the right, just like we are now in the introduction. And now we are in the WEC, which is the wave energy converter section. In the rest of the presentation, I will often call the wave energy converter WEC. A WEC is a device that harvests the energy from the ocean waves, convert it into usable energy, and send it to the grid for public and private consumption. There is not one design of WEC, but many. That is why selecting the best pairs of WEC and location is an enormous challenge. Henceforth, the need of selection guidelines. Now, let's see the WEC selection guideline for an area with a uniform bathymetry. This goes with the assumption that the area is relatively small and that the wave climate is the same over the area. Here we go. These are the steps of the selection guideline to select WECs for a given area. The first two elements comes from the first classification of the WECs that can be divided into two components, the water depth and the depth of installation. Another major classification of the WECs comes from its orientation of installation. A WEC that needs to be parallel to the incoming waves is called an attenuator, whereas if it needs to be perpendicular, then it is a terminator. Eventually, WECs that work independently from the wave direction are called point absorber. WECs can also be limited in the wave power, height, and period, and certain areas may need additional features. Just like here, on the Gold Coast with strong storm, it is highly required from the WECs to have some storm protection. Well, now let's come back to our classification. Here is a set of wave energy converter with mixed characteristics out from the three classes. Now, let's consider a zone with a uniform bathymetry of 40 meters. This is related to the nearshore WECs. Therefore, the only device offshore is removed from our selection. Now, let's consider that the zone is characterized by some protected marine life. We assume that it does not allow the installation of seabed devices. Only for that, all the other devices should have their moorings not taking a large space on the seafloor. Finally, we know that due to this protected marine life, the town is extremely touristic, and so to attract tourists, the town needs a wave farm not to be visible. Therefore, all the devices above the sea surface should be removed from our selection. Now we are left with two devices. And in fact, our research found that the annual energy production are very similar. The annual energy production, or AEP, is the amount of energy produced in a year and is one of the major metrics used to compare WECs. Fact is that, to the day of today, WEC orientation has little investigation in the research, and so AEP is mostly calculated regardless the WEC dependency on the wave direction. However, we can see for our zone that the distribution of the wave direction of our wave climate is quite broad. Here we have two peaks, for instance. So it is reasonable to conclude that AEP3 of WEC 3 is actually overestimated, and so we are left with WEC 5 for the installation of a wave farm in our zone. So far, we have seen how to select a WEC for an area with a uniform bathymetry. However, if the bathymetry is not uniform, allowing us the absorption of a large area, the problem is no longer reduced to finding a WEC for a zone, but to finding the best pairs of WEC and location for that given zone. And so another stepwise selection must be done. This is the decision tree, under the umbrella of the decision-making process. For that, more information are required to investigate the area. So far, generally speaking, the researchers are preselecting the hotspots based on high wave power or high energy demand, with some concern about the restricted area, such as, for instance, the consideration of the Great Barrier Reef, where you cannot put a wave farm, obviously. And then they would look at the annual energy production and other selected economic indicators to compare several WECs, and to define what is the hotspot. In this research, as you have seen before, we prone the need to select this hotspot with straightforwardly regards to the WEC characteristic and not taking it out from the hotspot selection. This leads us to the decision tree, which steps are provided here. In this tree, the final hotspot shown in the decision-making process is related to the last cell of the decision tree, after the application of all the filters like the water depth. The middle WEC ranking cell is not a hotspot selection, but it is only based on information that are countable, such as the annual energy production, the energy demand, etc. This allows to see the results before the application of the filters related to the area analysis and the water depth, as done for the WEC Selection-Guideline before. This will give maps with area of common best WEC that may overlap. The final step is to calculate the final selected economic indicators for the wave farm here, that can be installed within each cluster of WEC cell. For instance, using AEP as a selected economic indicators, the last step is to compare these AEP to select the most interesting pairs of WEC and location. So for instance, this and that one could be selected, or maybe this one and that one, having in mind that maybe one will be reduced to the limitation of the other one. Now, let's come back to our decision-making process and its relation to the decision tree. First, we need to obtain the wave characteristic map, including the wave climate that may change over the area. For that, measurements can be used, or if not, they can be obtained by a global wave model or generated using models like SWAN or MAC21. Obviously, the model needs to be validated. Now the wave characteristics are used for both the wave direction and WEC ranking, such that this is where information from the WEC are required to estimate the wave direction impact on the annual energy production. This energy production is later used to rank the WECs for each bin of the considered zone. The energy demand is also an information to integrate when ranking the WECs, such that, for instance, Producing too much or not enough energy seems to be less appealing than producing what is necessary. Eventually, the restricted area are considered as filter of the area analysis, just like the consideration of tourism limitation, for instance, like we did in the selection guideline. Here again, as seen for the WEC selection guideline, WEC information are necessary to apply the different filters as well as for the water depth. The wave farm design and overall annual energy production will also depend on the characteristics of the WEC, such as its size, for example. Like the size and the WEC functioning will play on the distance between the WECs. That is why it will affect the farm organization, including the number of WECs contributing to the overall farm wave energy production. Therefore, the WEC information are necessary in most stages of its selection for an area. Hence, to select a hotspot for wave energy conversion, wave energy converters information matters. Thank you very much for your information.